Welcome, class. Today, our lesson is on section 8.4, which I'll be assigning today as well. We do 2 class periods from today. So I'm assigning it here on this Monday, making it due technically next Monday, the Monday after Easter. All right. Our work today is primarily working with radical symbols, combining them, reducing them, a lot of possibilities. One of the most important rules that we're looking at today for algebra is if I have the nth root of something times the same nth root of something else, that's no different than a to the 1 over n, because it was a to the first here, that's the fractional exponent. This nth root of b can be thought of as b to the 1 over n. That can be written as ab both to the 1 over n power, or the nth root of ab. That's kind of your algebraic rationale behind it. But what I'd really like you to notice is that the product of these two is equal to this here. The nth root of a times the nth root of b is equal to the nth root of ab. That's going to be a very, very key identity for us that we need to be comfortable with and be ready to use. Here's a numerical example. This is not a proof, but it does check out. The square root of 4 times the square root of 49. Well, if you multiply 4 times 49, you will get 196. But now if you were to take the square roots, the square root of 4 is 2, the square root of 49 is 7, the square root of 196 is 14, 2 times 7 is equal to 14. Those happen to be perfect squares, but even if they're not, again, I want you to pay special attention to that identity. Square root of 2 times square root of 3 is equal to the square root of 2 times 3, or 6. If you look at the approximations of these, the square root of 2 is approximately 1.414. That's been rounded off. Square root of 3 is 1.732. Square root of 6 is, 2.449. Well, if you multiply 1.414 times 1.732, you will end up getting the 2.449. Again, just showing numerically that this particular one seems to hold for those. We'll be using this process in reverse frequently. First of all, I'm just trying to hammer a lot of examples. Here's the identity that we had. Using it in reverse means I'm going to take the nth root of something and I'm going to break apart the factors. So for example, this was the way we've been doing it. Radical 3 times radical 7 equals radical 21. Radical 5 times radical 11 equals radical 55. Third root of 4 times the third root of 6 equals the third root of 24. But now the other way, where I break it apart. An example would be radical 14. I can factor it into radical 2 times radical 7. Radical 18, I can factor it into, or the fourth root of 18, I can factor it into the fourth root of 3 times the fourth root of 6. This process, where I factor it down, is an important process that we use when we are looking to simplify a radical. Notice that this one could have been written also as the fourth root of 9 times the fourth root of 2. I emphasize that because sometimes there's more than one possibility. Sometimes one is useful, the other is not. We're looking at reverse here again, so we're looking at this second one where I'm looking for factors. As I mentioned, sometimes we can use it to simplify radicals. For example, the square root of 12, if, this is not always possible, but if you can find a perfect square that's a factor, that perfect square can be reduced. That reducing of that perfect square is the process of simplifying the radical 12. For example, radical 12, one of the factors could be 4 times 3. 4 happens to be a perfect square. Well, let's make sure we understand what we mean by perfect squares here. Perfect squares would be numbers like 4, 9, 16, 25. This is 2 times 2, 3 times 3, 4 times 4, 5 times 5. The next one would be 36, 6 times 6, 7 times 7, 49, 8 times 8, 9 times 9, 10 times 10, 11 times 11, and 12 times 12. These they would kind of like you to have down by memory. They're all perfect squares. I happen to choose the 4 here. Well, because the 4 can be reduced down to 2, this becomes 2 times radical 3. So the radical 12 here, we reduced it down to 2 radical 3. That may or may not look like it's simplified. Excuse me, but it actually is. Notice that I could have gone up here with radical 12, and I could have said radical 2 times radical 6, but neither one of those would have been perfect squares. So that would not have allowed me to get rid of one of those radicals. It wouldn't have done me any good. I had to use radical 4 because that was one of these perfect squares. Many of you have done this process in high school, so it should be reviewed. But I know there are some high schools that don't teach that anymore, and most textbooks are still wanting it to be done. I would like you now to take a look at all of these. And I would like you to try and reduce each one down, show the 2 radicals, and then show the perfect square being reduced down to another number. For example, here's what I would like you to show. I'm going to take 8 and factor it into 4 times 2. The square root of 4 is simply a 2. And that would be my reduced answer. I'm going to give you a head start, but I would like you to try the next 5 and go ahead. Here's the answers written in just a little bit clearer form. But in all cases, I showed the factorization that I was using. Let's take now just a few of them that have slightly larger numbers. Try these 4. I'll give you a head start. And again, here are those answers written in just a little bit simpler form. The key is always, again, thinking about these perfect squares. Which one of those will happen to go into the argument that we began by? That's what we're looking to do every time. Sometimes, however, there's more than one way to do it. Consider radical 72. If I look for perfect squares that will go into that, there's a lot of possibilities. 4 is a perfect square that goes into that. 9 is a perfect square that goes into that. And I'm thinking 36 is another perfect square that goes in there. All of those could be used. The best one is the largest number, 36. If I break it 72 down to 36 times 2, the 36 has a perfect square, 6. So my answer is 6 radical 2. As I mentioned though, 9 could also have worked. 72 could be 9 times 8. And it looks like you would get then 3 radical 8. And the question would come up, well, that doesn't look like it's the same answer. Well, technically they are equal, but this would not have been reduced down as far as it could. It would only be partially reduced. What we would have to do instead is we still got to reduce this radical 8 down. So 3 times radical 8, because radical 8 has a factor of 4, I could break radical 8 down to 4 times 2. The radical 4 is a 2, so then it's 3 times 2 times radical 2, giving me my final answer. Notice it was the same. It could have been gotten in either method, but again, notice the larger perfect square you can start with, the quicker the process goes. Another option would have been to start with 4, as you can see I did right here. Then the 4 is a perfect square. It gives you 2 radical 18, but 18 can be broken down again. 18 can be thought of as 9 times 2. Square root of 9 is 3, so multiplying those I get 6 radical 2, just like I had on the early one. So here was an example where I had 3 possible ways to do it. Sometimes there's only one way to reduce it, sometimes 2, sometimes 3, sometimes more. But again, if possible, start with the largest square that will work. I would like you right now to try and do it 2 different ways. 48 does have more than one possibility. I'm going to give you some time. Try to do it once 2 different ways. There are two perfect squares that go into 48. One is the number 16. The other is a number 4. 16 goes into 48 3 times, so 16 times 3 gives you the 48. But the square root of 16 is a perfect square, 4. And that would be my answer. But I could have started with the number 4, because 4 times 12 also gives you 48. Square root of 4 is a perfect square, which is 2. So radical 4 times radical 12 would become 2 radical 12. But then radical 12 you can reduce down again, because 12 could be thought of as 4 times 3. Square root of this 4 is another 2, so I got 2 times 2, giving me 4 radical 3, the same answer that I had over here. This next part's a little bit tricky. It kind of has to do with the concept of the square root of a number that's a perfect square. We sometimes will call it 5, sometimes we'll call it a negative 5. And both work because 5 times 5 does give you 25, which means 5 has to be the square root, but also a negative 5 times a negative 5 is equal to 25. Usually, when there's numbers involved, for example, the square root of 36, they're implying the positive root. If they want you to write the negative, they usually put the negative out front. But with variables, there's more uncertainty. For example, the square root of x squared, we usually begin by thinking, hey, x times x gives me x squared. That would imply then that this square root of x squared must be x, which is true. But just like we have the negative possibility, we notice that a negative x times a negative x gives us x squared. That leads us to think the square root of x squared is a negative x, which is also true. Just like up here could have been 5 or a negative 5. Both are correct. So we're going to try and show an answer that reflects both. And we do that by putting the absolute value of x as the solution, because that means both x and a negative x could be put in there, and we would be guaranteed to get the x squared. So anytime I break a perfect root that has a variable involved, we give the answer as a square root, provided I'm looking at an even root. What do I mean by that? Well, an even root would be a square root, or a fourth root, or a sixth root, or an eighth root. With odd roots, I won't have to do that, as we'll notice here in just a moment. This one is an even root. It's a square root. Because the 2 is even, it's an even root. So I'm looking for x to some power times itself, x to what power times the exact same thing would give you x to the 6. These two question marks have to be exactly the same. When you're multiplying bases, you add the exponents. So you're looking for a number plus a number that gives you the exponent 6. That, of course, has to be 3. We recognize that it could be a positive or negative, so because it was an even root, because it was a square root, I had to put the absolute value signs in. I'm looking for x to some power times x to some power, that gives you 8. Two numbers that would be added together would be 4 plus 4. Again, because it's an even root, I need the square root symbol. Be careful on this one. It's an easy one to make a mistake. I need a number added to itself that gives you 64. The correct answer is 32. A lot of people would have been tempted to go x to the 8 there, but remember it's being added, okay? Well, if I want to reduce a radical down, and this one happens to be an even radical, square root, I need to pull out a perfect square. A little tougher now. I'm not looking at numbers like 4 and 9, but I'm looking at numbers that if added to themselves would give me 7. For example, I can break x to the 7th down to x to the 6th times x to the 1st. Because when you multiply, you add the exponent. 6 plus 1 would have given you 7. But then the square root of x to the 6 is x to the 3rd. Because x to the 3rd times x to the 3rd gives you x to the 6th. And we needed the absolute value signs with that. This one's a little bit tricky again, as I mentioned before, but what I'm looking for is what perfect square can I take out of there? Well, don't be deceived here, but watch what I'm doing. X to the 16th is a perfect square. Not because of 4 times 4, but because in this case of x to the 8th times x to the 8th. The extra x, because I had 17 of them, I've got 16 of them here, 1 there. What power in here, when added to itself, gives you 16? The answer is that power needs to be an 8. Again, a lot of people might have put 4 there, so be careful for that. Remember, we're adding them. We're adding them. Remember, x to the 8th times x to the 8th. We add 8 and 8 to get x to the 16th. That's why the square root was x to the 8th. Taking that at a little bit more advanced level, in this particular example, I need to take the radical 8 and I'm breaking it apart into a 4 and a 2. I need to pull out a perfect square from x cubed. It would be x squared, and I got 1x left over. I need to pull out a perfect square of y to the 7th. It would be y to the 6th, and I have 1y left over. This one already is a perfect square, so I leave it in the radical that has all perfect squares in them. Then the square root of 4 is a 2. I have the absolute value of x, the absolute value of y cubed, and the absolute value of z to the 5th times the square root of 2xy. That's what that looks like, and that's why my answer looks as it does. Okay? Try this one on your own. I'll give you a head start, and then we'll go on from there. And that's how you break it down. And again, that's why the answer is what I have written there. This again shows the breakdown of those radicals. A little bit more involved, takes a little bit more time. I've been mentioning that it's always about even roots. Well, take a look at this one once. This 3 is not an even root. This one doesn't matter so much, but this makes it an odd root, that 3 right there. Well, the cube root of x cubed is x because if I take x times itself 3 times, I get the argument x cubed. So the cube root of x cubed is x. Notice I do not need any absolute value signs. If I have a cube root of a negative, we actually can get that value as well. It's a negative x because negative x times negative x times negative x gives you negative x cubed. So in this case, I don't need to worry about absolute value signs because these represent two different problems. The cube root of a negative x to the 6 is still going to be a negative. Negative times a negative times a negative gives you a negative, but it's x squared because 2 plus 2 plus 2 gives you the 6. That's another level of pulling it all together. It's a little bit tougher, I know that. Notice no absolute value needed when it's an odd root. Here the n was a 3, so I did not need any absolute value signs in my answer. With an even root like 4, the fourth root's an even number, then I need the absolute value signs. And the answer was x cubed because 3 plus 3 plus 3 plus 3 4 times gives me the 12. I needed the absolute value signs. Make sure that you keep the difference between the two. Well, let's do just a few more examples here. I need fourth roots, perfect fourths, if you can think of it that way. So I want to look, is there a perfect fourth in 32? Well, perfect fourths, one of them would be 2 to the fourth, which is 16. 3 to the fourth is 81. 4 to the fourth is 196. I'm looking for any of these numbers that would go into 32. Obviously, the 16 does. 16 times 2. 16 has a fourth root. It's 2. Fourth root of 16 is just the number 2. I'm looking for a perfect fourth for a to some power. Well, a to the fourth is a perfect fourth. A to the 8th is. A to the 12th is. A to the 16th, etc. I could keep going. The largest one that I can go with here is a to the 8th because that does go into a to the 11th. So a to the 8th, I'm left with an a to the 3rd left over. The largest one for 20, you have 4, 8, 12, 16, 20. That is a perfect fourth just the way it stands. D to the 22nd, I can take out a 20, but I'd be left with d squared. Then the fourth root of 16 is a 2. I have now an even power, so I need to go absolute value signs. I missed that one. That should be a fourth root, so it should be squared because 2 times 2 times 2, excuse me, when I'm adding exponents, 2 plus 2 plus 2 plus 2 plus 2, that gives you 8. So this would be c to the 5th, and it would be d to the 5th times the fourth root. This is what's left over, a cubed d squared. I'd like you to try this one next now. This one's a cube root. A cube root. Just in case you didn't get that last answer down here, maybe I can do that one here a moment. I'll put it up here while you might be working for the next one. One of the challenges with these is always knowing when do I have to add the numbers or when do I got to multiply them. For example, the 32 was 16 times 2, but 8 to the 8th times 8 to the 3rd, I added 8 plus 3. It has to do with those laws of exponents again. In case you didn't get those, here are those answers. And I forgot my absolute value signs on this one. The reason for those is this was an even number. I did not need them down here because I had an odd root. Our final concept, I got a few slides concerning this one, but it is the final concept. It's known as rationalizing the denominator. Rationalizing a denominator basically is just simply a procedure we use to reduce an expression which has a radical in the denominator. We sometimes say put it in lowest terms, simplify it, reduce it. It's when I have a radical in the denominator. For example, this one right here. I have a square root in the denominator and it's considered improper to leave it in that form. It would be considered unreduced. It would be kind of like leaving a fraction 6/8 instead of reducing it down to 3/4. This is considered the correct answer. This one is an unreduced answer. Well, if I leave a radical in the denominator, I have basically an unreduced fraction. We perform an algebraic trick here to get rid of that radical in the denominator. The trick really is this. I'm going to take this fraction, multiply it by a value that's equal to 1. Because if I multiply anything by 1, I don't change the value. Now in this case, I didn't even change the appearance. However, I'm going to choose a very specific 1. A lot of different ways I can write 1, but I could go 8/8, 15/15, radical 3 over radical 3. All of these equal 1. Anytime the numerator and denominator are exactly alike, the value is 1. And if I multiply by 1, I don't change it. So I'm going to choose a very specific one. Whatever radical I have here, I'm going to put that radical over itself. Don't miss this now. This is again, that parentheses is like a 1, which means I don't change the value, but I will change the appearance. I get 3 times radical 7 in the numerator. The denominator becomes radical 49, and radical 49 reduces down to 7. I cannot cancel those 7s because one is a 7 to the first, the other is a 7 to the 1/2. Notice again, I multiply. This is again showing the exact same thing. Don't miss the fact that this parentheses is equal to 1. And when you multiply by 1, you don't change the value. Here I multiplied by 1. The value of this is exactly what it started. It just looks different. This is considered to be reduced because there's no radical left in the denominator. Now, people would argue it looks more complicated than that, but the point is we got rid of the radical in the denominator. These are our last 4 problems. This one right here, I'm going to multiply by a 1. I'm going to make the numerator and denominator exactly the same. And I make them the same as whatever that radical was in the denominator. Then my numerator becomes a -5 radical 3. Radical 3 times radical 3 is radical 9. So I end up with square root of 9 here to be 3. This one, I'm going to multiply by 1. That means the numerator and denominator have to be exactly alike. I want to get rid of the radical in the denominator, so I choose the radical from the denominator to put in both of these. Again, remembering the parentheses is 1. This numerator, 7 times 5 here, they're both radicals. Radical 5 times radical 5 would be radical 25. So I would get radical 35 over 5, and that would be my answer. The next ones are more challenging because they're not square roots. It's easier for us to work with square roots than a cube root or fourth root. But the procedure involves the same concept. I'm going to multiply by a 1. But here's where it gets to be quite a bit tougher. In the previous example, I chose radical 5 here because I knew when I multiplied those, I get a perfect square, 25, which I could then get rid of the radical. I need a perfect cube here. Two times some cube root has to be a perfect cube. Well, what are the perfect cubes again? Well, 2 cubed was 2 times 2 times 2, or 8. 3 cubed was 3 times 3 times 3, or 27. 4 cubed was 4 times 4 times 4, or 64. 5 cubed, 5 times 5 times 5 is 125. I'll stop there. 2 times what would give me one of those numbers? Well, I'm going after the 8. So I need 2 times 4, because that would give me a perfect cube of 8 over there. So I had to come up with the number 4. If that's what I put in the denominator, remember these have to be the same like they were here and here. So I need the cube root of 4 there. My numerator will be 10 times the cube root of 4. That's not a perfect cube, but the denominator is. So my numerator stays exactly the same, but my denominator would have been a 2. And now I could have also reduced 2 into 10 and gotten 5 cube root of 4. Cube root of 4 cannot be reduced, however. Okay. I'm going to leave the last one off. That's a poor example. So we're going to leave that one off a moment. That is all we have for our lecture today. We're assigning again section 8.4, and I'm assigning that on this Monday, making it due, because we don't have school on Friday, I'm making it due next Monday, the Monday after Easter. Have a good rest of your day.